Now, remember, what we are dealing with, first of all, is a simple regression model. A simple regression model. In other textbooks, it will be called a bivariate model. Okay, bivariate model. Okay, bivariate, simple or bivariate regression model. Let me write it properly. Simple or bivariate regression model. Okay, so where we said we will have something like this. Okay, beta naught plus beta 1 x plus mu. Okay, why are we calling it a bivariate? Because there are only two variables, one dependent, one independent. Sorry, one dependent and one independent. Okay, now we talked about the components of this model, and we were interested in one of the things we're interested in the parameters beta naught and beta 1. Okay, so remember, these two are important in a simple regression model because they tell us how all right. So what I was trying to say is that for the two, as you can remember, one of these, beta naught tells us how much how much y will be if x is 0. And we said for beta 1, it says how the dependent variable will vary as a result of a 1 unit change in the independent variable, whether positive or negative change. Okay, how it will change. That's what these two tell us. And then what I was explaining also is that remember what we discussed yesterday is what we do is simply get estimates. Okay, we cannot measure the exact relationship. It's rare that we find ourselves measuring exact relationship between two or more variables because of the reasons that we gave yesterday. Okay, things like measurement errors, omitted variables, okay, vagueness in theories, so to say, things like measurement errors, okay, and so many things. Okay, there are those things that cannot be quantified but would affect the dependent variable, all those things. So usually what we do in regression analysis is just simply getting estimators, okay? Estimators of beta 1 and beta 2 in a case of bivariate model. And like I mentioned yesterday, there are a lot of methods that we use to estimate this, but the one that is commonly used because of its advantage over all is what we call the ordinary least square method. This is what we are interested in today. Okay, so okay, so we begin the ordinary least square, like I mentioned yesterday, begins by minimizing. It minimizes the sum of error squared. That's what it does. Okay, what is the error? Like I mentioned yesterday, the error is just simply the difference between the actual and the estimated. The difference between the actual and the estimated. Okay, so remember where this estimated y is the same as the beta naught estimated plus beta 1 estimated x. Okay, just like that. So what are we saying? So if we're minimizing the sum of error squares, we are saying we are minimizing, okay, the sum of error squared, which means what we are minimizing on the other end also is the sum y minus y hat squared. Okay, this is what we mean. Okay, we are minimizing that. Okay, so now in our case, given that this here is okay, y hat is that, we just replace there. So intuitively what we are doing is minimizing okay, y minus beta naught when we replace, okay, replacing this right here with this. So we're saying beta naught minus beta 1 hat, okay, x and all squared. Now, like I mentioned, the concept of minimization in calculus, okay, the concept of minimization in calculus, what we do, I mean, the concept of minimization is the calculus concept, all right? So what we usually do here is we partially differentiate
before you
the
proceed.
sum of error squares.
Before you proceed, sorry.
Yes, please.
Just take the board a bit up. There's a positive sign on beta 1. We still maintain the negative.
Yes, it's negative. Why? Because initially what I did here is I replaced, I'll put it in brackets. So beta naught hat plus beta 1 hat x. Okay, I'll put it in bracket because this here is what this is.
Okay.
So yeah, but there's this negative. So that's why, okay, I think I'll keep it like that. Is that negative there? So that's why we're saying sum error squares is equal to y minus beta naught hat minus beta 1 hat x squared after we open the brackets there.
Okay. Okay, better that way.
Okay. Yeah. Okay. All right. So like I was saying, when we are dealing with calculus, what we are doing here in the case of ordinary least squares is that we are minimizing the sum of error squares relative to the estimators, okay? Relative to the estimators and equating this to 0. Also minimizing, okay, sorry, to the estimators. So we have beta naught there and also we have beta 1 estimated, okay? So this is important. I need to make mention these notations are important, okay? These hats are important just to show that this is an estimated model. Okay, that's what we're saying. Okay, now maybe just a recap on
where are we getting those
which ones?
These two, just on top there. Just explain a bit where we're getting those. There's some of estimated squared. Sorry, there's some of is it the
So what I'm saying is this. So the concept of ordinary least square method, okay, is a concept that minimizes the sum of error squares because now we would want to estimate. Okay, let me put it this way. When we want to understand the relationship between two variables, right? But what helps us in understanding the relationship between the two variables is these beta naughts and beta 1. So intuitively, what we are doing is we would want to know how do we get this beta naught and how do we get this beta 1. So for the ordinary least square method, what it does, it minimizes the error to get beta naught and beta 1. Okay, it minimizes the error to get the beta naught and beta 1. So what error are we talking about? The error is just simply the difference between what is the actual and what is the estimated, okay? I think I explained this in yesterday's class. Why are we saying this is the case? Because if in the absence of errors, we'll have the true relationship. But because of those other variables that we mentioned that affect our estimation, we have only estimated models. Okay, so the difference between the two is what we get the errors. Is the errors, sorry. So now for the ordinary least square method, what it does, it tries to make this as small as possible, the error as small as possible, so that our estimators are close to the actual relationship as close as possible. That's what it does. Okay. I don't know if that answers your question.
yes, but just go on, just slightly under.
All right.
These two.
Which two? This one here.
No, they're just down there.
This
what
one.
I,
To this
yeah.
one and there. Yes,
This one.
yes, this one. Yes.
Yes. So like I was saying, minimization, when we say minimize this, minimize that, in calculus, it's just simply differentiation. So this is
No.
derivative of this sum of error squares with respect to beta naught, and the derivative of this sum of squares with respect to beta 1.
Okay. Okay.
Yeah, you get the idea.
I get the idea. Yes.
Okay. Any other question? All right, please ask. In case we miss it here, it becomes a problem. So in case there are questions, please feel free to ask. I've seen Mr. Mchochoma asking about this in most of the papers. I'll show you some. All right, so recap on calculus. Now here I shouldn't take more than 5. Okay, let me say I shouldn't take more than 10 minutes on. N, where A is a constant and also N, okay, N is an index, okay, an index, okay, which could take any value, okay, So if we're given a function like this, to differentiate, okay, okay, what we do is we multiply the index by the whole function, okay, we say to differentiate, okay, let me say proceed as follows. Okay, so we're saying y is equal to y is equal to axn. Let me write it properly, the whole thing. And then what we do for the notations, we can have dy dx, meaning we're differentiating y with respect to x, or simply y prime. It just simply means you're differentiating y with respect to x. So this will be equal to, so we'll multiply this here to the whole thing here. So we'll say n times a x n, then less the power by 1. Okay, so we less the power by 1. Okay, for example, if we have y is equal to 3x squared, for example, okay, so to differentiate, we are saying y prime is equal to, this 2 comes down or multiplies with this here, which is 6, okay, and then x, and we say we reduce the power by 1, so which is just simply 1 there. Okay, another example, just in case there are those that are still wondering what's going on. So if we say y is equal to 12x to the power 5, for example, to get y prime, we're saying this is equal to, this comes down here, multiplies with this, so we have 60. And then we say x to the power 4, since we less it by 1. This is what this concept is saying. Okay, this is what this concept is saying. This concept is called the power rule. Okay, the power rule of derivatives. Okay, this is the power rule of derivatives. Okay, we're following that.
Yes.
Okay. So now Then we have what we call, supposing now that we have, say, y is equal to a times open bracket f of x to the power n. Okay, instead of having a variable here, now we have a function, and then it is raised to some power. Okay, so here what we do is we make use of what we call the chain rule. Why chain rule? Because we have a chain in our case here. There's a function multiplied by a constant, and this very function is to a power. Okay, so we use chain rule. So by chain rule, what we say, we go with the power rule first. Okay, we go with the power rule. So y prime is equal to this n multiplies with that a. We're saying a n. Okay, the whole thing. Okay, f of x, and then we less this n by 1. Okay, so what we have applied here is the power rule. But in addition to this, what we do is we multiply by the derivative of what's in the bracket. Okay, f prime of x. This here is the chain rule. Okay, for example, so let me emphasize this thing, that this here is a constant. Okay, this here is a constant. Okay, if it's a variable, it becomes different. This rule becomes different altogether, or the procedure becomes different altogether. So this is a constant. Okay, so let me give an example. Y is equal to open bracket 2x plus 3, okay, to the power 3. Okay, to the power 3. And then let me say 2x squared. Okay, so to differentiate this, what we are saying here is y prime is equal to 3. Okay, this comes down, multiplies with this one here. Okay, there's a 1 here, which is invisible. So we'll say 3, open bracket 2x squared plus 3, then raise to the power 2. Okay, but remember, we are multiplying with the derivative of what's in the bracket. So what's in the bracket is this 2x. Okay, so 2x squared plus 3. So the derivative of this 2x squared plus 3, okay, this is equal to, so this 2 here multiplies with that one here. So we say for x, we less it by 1. Okay, so it's x to the power 1. Then the derivative of this one here is 0. Now, which brings me back to this point. Derivative of a constant, NB, derivative of a constant is 0. Okay, the derivative of a constant is 0. Okay, so this is what happens. Okay, this is what happens. So in this case, we are adding plus 0 because the derivative of this 3 here is 0. Okay, so what does that mean? Y prime is equal to 2x squared plus 3. Okay, multiplying 4x. Okay, x to the power 1 is just simply x. So the 2, this one here and this one here can multiply. Oh, by the way, there's this 2 here, which I forgot. So this here can multiply with that, and we are saying prime is equal to 12x, open bracket 2x squared plus 3 to the power 2. Okay, I hope I'm not too fast there. Hello?
No, we are together.
We're getting you.
All right.
Are we,
Okay.
Mr. Manama?
Yes, please.
Yeah, are we able to compute how we are getting a 0, or just to say the derivative of a constant is 0? Or maybe we can put
Okay, let me give an example. Okay, let me give an example. The intuition is this, huh? The intuition is this. Okay, the intuition is this. Let's take the same 2x to the power 3 plus plus 3. Is it true that this 3 is the same as 3 times 1?
Yes.
It's true, not so. 3 times 1 is 3. So if we want, if it could have been this, not so.
Yes.
I mean, this here is the same as this here, not so.
Yes.
What are the possibilities of getting 1? The possibilities of getting 1 here is that this is x to the power 0, not so.
Yes.
Okay, it's x to the power 0. Right? Any number to the power 0 is equal to
1. Yeah.
1, not so. Right?
Yes.
So if that is the case, now if we were to differentiate this part here, because this is x to the power 0.
Oh, yeah.
So remember, when we're differentiating, this comes down. Okay, so we have two. That means since this one is also differentiating, so this is 2 times 3x, okay, plus when we differentiate this here is 3 times 0, and then we are saying x 0 minus 1, not so. So we're saying this here is 6x plus this here is 0 times x to the power negative 1, which is equal to just this, not so.
Yeah, okay. All right.
That's the whole intuition. Okay, that's the whole intuition. Okay. Okay, so yeah, that's the whole intuition here. So what else is left here? Right. Okay, like I said, this is just a recap. I'm not going into detailed in the area of calculus. I think it's a vast area. So I'll just pick what is important, and what I've picked so far is, maybe let me just mention one more thing. That is partial differentials, partial differentiation, rather. Differentiation. Or let me just say partial derivatives. So when we talk about partial derivatives, okay, sometimes we have a function of two variables, okay? We have the function of two things, okay? Two variables. How do we differentiate? How do we differentiate function of two variables? Okay. Even more, there could be more, okay? But I'll just stick to two variables. Okay, there could be two or more variables. So, for example, if we have f of x and y being equal to ax to the power n plus, or it could be even products or whatever it can be, okay? But this is just for the purpose of giving examples. So plus b y to the power m, for example, okay? To differentiate, what we do, okay, what we do is we differentiate the whole function with respect to one variable, holding the other one constant, okay? Differentiate, then again differentiate the other variable, holding the other one constant, of course separately, okay? Of course separately. To differentiate this, what do we do? So we say f prime, in case we're given a function like this, we're saying f prime, say x, we show like this. So which means derivative of this function with respect to x is equal to, so we'll hold this one as a constant, okay, and differentiate where we have n. So we're saying a n, because this comes down here, okay, because this comes down here, and then multiplied by x then less by 1, less the power by 1, just like we have done so far. Okay. And also when you differentiate the other part, of course, it becomes 0. Why? Because we held this as a constant. So a derivative of a constant is what? Is 0, not so. So an xn minus 1. That will be the derivative, not so.
Yes.
Yeah. Okay. So let me give another example for the purpose of now. Okay. So we differentiate this function with respect to x. Now we differentiate it also with respect to y. Okay. So what do we do? So we hold this x constant. Now we only deal with y. So that being the case, the derivative of this part here becomes 0 because we've held it constant. And then we concentrate on this part here. Okay, so that we have plus b, okay, times m. This m came from here. And then we less m minus 1 for the power there. So that the derivative of fy, okay, is equal to pmy m minus 1. Okay. That disconnecting us. Otherwise, I apologize. I hope this is. I continue the recording. Is it recording? Yes. Okay. Is it? Today we're okay. The number is really small today. Huh?
I don't know what has happened. People were in, but they've just disappeared. I think I saw Senga somewhere, even Niabi, but I think they're not to be seen. Maybe it's network issue.
Okay. All right. So up to here, do we have any questions?
Up to
No
here,
questions
no.
here.
So far, so good.
Okay. Okay. So these, I think these will be enough to apply to what we are about to do. So let me get back to who is that? Okay. So remember what we are doing here, okay, is just simply trying to okay. So what we're minimizing is this, and then yeah, this symbol here just represent partial derivative. Okay, don't know if you remember. So this means just partial derivatives. So now, so like I said, we are minimizing the sum of error squares. We're differentiating this with respect to beta naught and with respect to beta 1. Okay, so we begin with beta naught. So what is the partial derivative of this here? Okay, so now from what we've just learned, okay, we say this here, if you can see, it's a chain function, not so, right? Because it's raised to the power 2. Have you seen that? No? You seen that? So if that is the case, when we're differentiating that, we say this here comes down, which is 2. Okay, we say summation, we write everything the way they are. Y beta naught hat minus beta 1 hat, okay, x, okay, and then less that power by 1. Okay, this is by 1, so I've raised the power 1 there, and then we multiply this here, okay, times the derivative of what's in the bracket with respect to beta naught. Okay, so what we are interested in is where we have beta naught. The rest we hold them constant. As long as there's no beta naught, we hold it constant. Okay, so beta naught is here, it's negative beta naught, so derivative of that here is negative 1. Okay, that is negative 1. Okay, So what does that mean? Okay, also equate it to 0 because that's what the condition tells us. We need to equate it to 0. Okay, so after that is done, what we have on one end is -2. Oh, no, let me take it easy. So given this derivative that we've had, we've used chain's rule. So I'll say by chain's rule here, by chain rule, this is what we got. Okay, so we brought these two down here. Okay, we brought it down, placed it by 1, then multiplied by the derivative of what's in the bracket, just like we had shown in our case here. So we differentiate this. We brought down 3 here. Okay, brought down 3, and then leave everything less in the bracket and list this one by 1. But again, we multiplied this whole thing by the derivative of what's in the bracket with respect to x. Okay, it's exactly what we've done here. Okay, it's exactly what we've done in our case here. Okay, so we differentiated this function. These two came down. We have 2 summation open bracket y minus beta naught hat minus beta 1 x 1. Then we multiply this by -1. Okay, why -1? Because it's coming from the derivative of negative beta naught. Okay, because we're differentiating it with respect to beta naught. Okay, so to simplify this, we just simply multiply this and that. Okay, just simply multiply that, this and that. So we have 2 summation open bracket y minus beta naught hat minus beta 1 hat x, okay, to the power 1, and still equate it to 0. Okay, still equate it to 0. This here is what we call a normal equation. Okay, so I'll call it a normal equation 1. Okay, right. So are we together?
Yes.
Okay. All right. So if that is the case, okay, so from this point, what we just do is divide. Okay, divide both the right hand side, okay, left hand side and right hand side by -2. Okay, this -2 here, we divided both this side and the other side. So we have -2 summation y minus beta naught hat minus beta 1 hat, okay, x divided by -2 is equal to 0 divided by -2. This is what I mean there. So after that, so this and this go. So we have summation y minus beta naught hat minus beta 1 hat x, okay, is equal to this into that. We have 0. Okay, I hope we're following up to there. Just feel free to ask or slow me down in case I'm too fast. Okay, so that is that on this. So,
Mr. Mama,
yes, please.
do I have a point where to your right hand side you have a constant other than 0?
No, this is the first order condition. Okay, it's coming from this. This is the first order condition that for a maximum, okay, maximum or minimum, the derivative should be equal to 0.
Okay.
You get the sense, huh?
I get this.
So this is the first order condition.
So maybe it's just one way of removing the -2.
No, not necessarily. So the now let me say this point where it's equal to 0.
Okay.
Yeah, that's the same idea there. So there's no way this one will have a different constant other than 0. It's the first order condition. Okay, I think in a small way, that's how I can explain that. Okay, in brief. Okay.
Yeah. Now, before I was kicked out actually just after you did the normal equation 1. I was kicked out of the system. Now, just take me through where you are dividing by -2.
Okay, so in this case, because we have this constant here, which is multiplying with that function and is equal to 0, this constant is a factor of 0. So we can just simply just divide throughout. This is what we've done here.
Okay.
This is what we've done. So we just divided this into that. And what we do on the left-hand side, we also do on the right-hand side. So we divide both sides by -2. This is what we have, and the result is what we were about to write here, which is equal to 0.
Okay. Okay.
So yeah. Now here we then look at the properties. Those caves I was drawing is just I was explaining a question by Mr. I don't know if it's Mr. Mukuka. Oh no, not Stanley. Mr. Cavasso. Yes. Yeah, there was a question to say, is there a point where we only have, we have a different constant, okay? I mean, we have 2 instead of 0 here. So what I was explaining is that these are first order conditions, okay? It's always supposed to be 0. So there'll be a point where the error is almost equal to 0, or let me say it's equal to 0, and that's the point that we're looking for. Okay, that's the point that we're looking for. Okay, so I gave an example, a practical example. Of course, away from this, it's just something that will help guide our intuition. So there'll be. So now, what do we do from this point? Okay, here we cannot say divide both sides by summation. No. Okay. We cannot say divide both sides by sum. Okay. So why? Because this is an operational sign. This sigma here, it's an operational sign. Okay, same as times. Okay, it's same as pi. In some instances, it means multiplication. These and these are equal. So if you're saying sum, we're saying add the distribution. Okay, so that's what it means. So we cannot really divide throughout, but instead, what do we do? Remember, I think this is something that you've seen before, the properties of sigma notation.
Before
Okay.
proceeding, Mr. Manam, so a question can come in to say differentiate with respect to beta 0 or beta 1.
We come to say derive the OLS estimators.
Okay.
Yes, it's there in your in past papers. You'll find it. I'll show you.
Oh, okay. All right.
Okay. So now properties of sigma notation. Okay, properties of sigma notation. So we have y minus. Okay. What am I saying? Okay. So it's sigma notation. Now the first property, number 1, is that it's distributive. What do we mean? That summation of a plus bx, okay, is equal to summation a plus summation bx. Okay, this is what it means. Okay, so then property number 2 is that if a and b are constant, number 1, summation a is equal to n times a. What does that mean? The number of times that this a appears times a itself. All right. For example, if we have 2 2, 2, 2, 2. This bx, we can simply factor out this b and leave x with the summation. Okay, these are the properties of the
I think
sigma
you
notation.
had the network challenge. Sorry, we were cut just from the start. You said if A and B are constant, then you are cut.
Okay, so if A and B are constants in this example, this one explaining here, if A and B are constants, then summation A is equal to the number of times that A appears times itself. I gave an example to say if you have 2, 2, 2, 2, this here, summation 2 is the same as 2 plus 2 plus 2 plus 2 in this case, which is equal to 8, or simply just 4 times 8, 4 being the number, times 2, 4 being the number of times this appears times itself.
Okay.
So now there one thing I've forgotten, not forgotten, but one thing that you can see here is that this I is equal to 1 to 4. 4 being the number of observations. Okay, the number of observations. Okay, which is 4 times 2. So in short, what we're saying here is summation I is equal to 1 to n of A is equal to n times A. Okay, or simply, or also for the second part here, saying this runs from 1 to okay. Okay, so this runs to n. Okay, so B, sorry, what am I saying? Okay. Okay. B sub Bxi is equal to B summation n 1 to xi. This is what this means. I've just expanded this here, but if you want to keep things simple, this is just this here. Now I just want you to get used to some of these notations. Okay, some of these notations. These are subscripts. They mean the same. These are subscripts. So subscript I there. Right. Okay, so those are the properties of the sigma notation. So now, what is the implication here? So the implication is that okay. So the implication is this: for what we have from this point, okay. So from what we have this point, the first thing is that sigma is distributive. So we're going to distribute this here. So we're saying summation y minus summation beta naught hat minus summation beta 1 hat x is equal to 0. So we've distributed based on the properties of the sigma notation. Okay. And then from this here, what we can see, remember, beta naught is the intercept, not so. From where we're coming from,
Yes.
beta naught is the intercept, not so.
Yes.
So we called it the constant yesterday, not so.
Yes. Yes.
Okay. So if that is the case, one thing that you can see here is that this here is a constant, and
Zero.
we'll apply this rule here. Okay, summation constant is equal to the number of times that that constant appears times itself, not so?
Yes.
Okay, so I say in summation y is minus n beta not hat, okay, minus, and from our other property here, since beta b is also a constant, beta 1 is a constant, okay, it's just a number that tells us the relationship between x and y. So we can also factor it out from this here, not so? From this here, not so?
Yes.
Okay, from our properties here,
Yes. Yes.
yeah. So we have beta 1 hat summation x, this is equal to 0. Okay, now here, how we progress from this point is we're going to rewrite the whole thing here in terms of n, in terms of this n that we've introduced, okay, so that we can we can factor out what is common among them. Okay, now this summation y is equal to ny bar. Why? From the first class, remember, summation y over n is the mean, not so?
Yes.
Yes.
So if we are to get summation, we're going to say divide by 1 and then cross multiply. Remember this algebra?
Yes.
Okay. Others, do we remember that?
Mm.
So this here multiplies with the denominator, this multiplies the numerator there, so that we have summation y is equal to ny bar. Do we remember this? Cross multiplication.
Yes, we do.
Okay.
Cross multiplication we do. Is that y bar over 1?
Yes. It's over 1. Because saying this is equal to y bar. Okay. But if we want to solve for summation y, we say, okay, over 1, not so.
Yes.
Mhm.
Then we cross multiply. This is how come we have this here. Okay. So the same intuition goes with summation x. Summation x is the same as n x bar. Okay. Why? Because summation x over n is equal to x bar. Okay. So if we're to get summation x, we're saying over 1, cross multiply, we have summation x, okay, times 1 is equal to n times x bar. See that? Huh?
Mhm.
Yes.
Madam, are you following?
Yes, I am.
All right. Okay. So we just replace what we have here so that everything is uniform there. So therefore, we have ny bar minus n beta naught hat minus beta 1 hat, okay, and x bar is equal to 0. Okay. So that being said, from this point, what we do is we can factor out n because it's common throughout, not so? And n
Mhm.
is
Yes, it
still a
is.
constant also. Okay, so we are saying n, we factor out n, what do we have remaining? Y bar minus beta naught hat minus beta 1 hat x bar is equal to 0.
Zero.
Mhm. Then we divide n throughout.
And
Okay,
and
so we have y bar minus beta naught hat minus beta 1 hat x bar is equal to 0, because any number divided by 0 is equal to 0, including n
zero.
itself. Mhm. So from this point, we can make beta naught the subject now. Okay, so either this will go the other side or this will go the other side, but we will have beta naught there. Okay, so we'll take beta naught onto the other side. So what we'll have is y bar minus what remains there, beta 1 hat x bar is equal to beta naught hat. Or simply beta
Rearrange.
naught hat, yes, is equal to y bar minus beta 1 hat x bar. This is how you derive. This is the formula you're going to use to calculate for the intercept.
So what are you saying? So you have derived the beta naught?
Yes.
Oh.
Okay. Okay. Are we there? Questions?
Yes.
I think on the derivation, I'll end on this so that you practice it. From here, we're supposed to derive beta 1.
Beta
Okay.
1.
By differentiating, remember when we're partially differentiating, in this case, we had two things we're differentiating with respect to beta naught and with respect to beta 1. So since we are done here, we need to now differentiate with respect to beta 1. Okay. But for this is 2115
So,
to start with.
well, did
And
you
then
start
also, I think we're tired already. Yes.
when deriving the beta naught? Where did you start from? From which equation? Just go a bit up there.
With respect to 1, a beta naught, sorry.
Okay, which equation are we using?
I started with respect to beta naught here.
Okay.
With respect to beta naught. I just differentiated with respect to beta naught and then just simplified everything. Okay. Just simplified everything. Okay. Questions? If you feel safe, if you can feel
Yeah.
Okay.
You'll find it in 2-3 past papers, of course. You find this.
Yeah, driving is always there.
Practice more.
The best we can do, maybe